Okay, the floor is yours.
Hello everyone, nice to meet you in this conference. My name is Sung-Soo Lee, and I'm a PhD student at KAIST. Today I'll talk about security assessment framework for software-defined networks called Delta. This is a joint work with my colleagues Changhoon and Chani and Professor Shin, who is my advisor, and also Vinod and Peel from SRI International. The contents of this presentation are as follows. Let me start with a background. So what is SDN? Here we have a traditional network that we are familiar with, and each network device has its own control plane and data plane. But in SDN, the control planes are separated from the devices, and as you can see, since the control plane is now unified and centralized in this SDN controller, a bird's eye view of the entire network is also offered in SDN. SDN controllers can host useful and innovative network applications that provide flexible and dynamic network control. For this reason, SDN is known as a programmable network. SDN controller and the devices communicate via SDN protocols, and OpenFlow is a de facto standard. Although SDN offers the significant advantages over the traditional networking, the security of SDN has not been sufficiently verified. To give you one example, some of the popular SDN controllers are prone to this event listener subscription attack. In this example, we assume that a network operator has downloaded and installed a malicious SDN application because SDN application ecosystem is similar to the Android's in a sense that anyone can develop and distribute SDN applications using open APIs. So the malicious application accesses a packet notifier in the controller and removes the L2 forwarding application without any constraint. Next, host A tries to communicate with host B, but since there is no message flow rule, the switch does not know what to do with it. So it queries the controller by sending a packet message. Once the controller captures a packet message, the packet notifier passes the message to all the applications on the list. However, this list has been manipulated by malicious one. The packet notifier, the packet message is never delivered to L2 forwarding application. Thus, host A cannot communicate with host B. The attack example that I just mentioned in the previous slide is just one of many known attack cases. So the network operators who are seeking adoption of SDN would want to know if various SDN components are vulnerable to these attack cases or not. But reproducing each attack case in different SDN components is definitely not a simple task. And also, passing all the known attack cases does not necessarily mean that an SDN component is secure, as there may exist in unknown attacks. So today, I would like to introduce a security assessment framework for SDN called Delta that can not only reproduce known attack cases and also find new attacks. As briefly mentioned, one major feature of Delta is reproducing known attack cases. So here are the design goals that we aim to accomplish. First, when reproducing known attack cases, Delta should cover as many attack scenarios as possible. So currently, the number of the known attack cases that Delta can reproduce is 20. And it should be highly automated to minimize the human efforts. So it is conceptually similar to Metasploit or Nessus. Lastly, Delta should support various SDN components that, for instance, Delta now supports 4 popular SDN controllers, including ONOS and OpenALI. Another major feature of Delta is discovering unknown attacks. So, to cover the commercial SDN components that are usually closed source as well as open source components. So in our framework, we use a black box fuzzing technique, and with the black box fuzzing technique, we can find the 7 unknown attack cases. And in our framework, so we specifically aim to first test SDN control flows, such as OpenFlow operations in OpenFlow-based SDN. So I'll come back to this matter in later slide. So this is how Delta looks like. Delta consists of one agent manager and 3 different types of agent. application, channel, and host agent. The agent manager communicates with all the agents in the network using a dedicated Delta control channel, and this channel is shown as a red dot line in this figure. And as you may have noticed already, the agent manager is basically a control tower that controls and manages all the agents in the network. So the users would access the agent manager to configure and perform various security tests against the network. The application agent is an SDN application running inside the controller, and it includes various known attack scenarios that could be performed by an SDN application. And also it has a fudging module that can sniff, intercept, and forge and change the SDN control flows to find new vulnerability. The channel agent is located between a controller and a switch, and it also comes with a fudging module that can sniff and modify the ongoing SDN control flows in the channel between the controller and the switch. Lastly, the host agent acts as a normal host participating in the target network, and it is capable of generating network packets to any accessible targets. For instance, the host agent may send a large volume of network traffic to an SDN-enabled switch device, causing a packet inflooding attack. So here is how Delta basically works. As I briefly mentioned, Delta offers two different operation modes, reproducing known attack cases and finding unknown attacks. So first, a network operator can choose one of the modes, and in the case of the reproducing mode, the operator has to select attack cases as well. Then the agent manager instructs each agent to take different actions according to the test scenario. And when finding unknown attack cases, the fudging modules in each agent randomize the SDN control flows from their location. After each test case is done, the agent manager collects the test result from each agent and then analyzes it. Finally, the agent manager tells the network operator if the network has passed the test cases or not. From now on, I would like to talk about the black box fuzzing technique used in Delta. To more efficiently and systematically randomize the SDN control flows, we first classified the control flows into three different types based on each operation. So we have symmetric, asymmetric, and intra-controller control flows. The first one is the symmetric control flow, which is a request and reply pair. So if a controller or a switch send a request message to the other one, the receiver has to send a response message. Another type of control flow is the asymmetric control flow, which is a unidirectional message. Lastly, we have the intra-controller control flows, which are actually OpenFlow related API call chains between SDN application and core services provided by the controller. So leveraging the three types of control flows, we derived an operational state diagram of a typical SDN controller as shown in this figure. So in this diagram, a state labeled R stands for ready state to receive or send control messages, and the other states are labeled in accordance with the type of control messages. So based on the state diagram, each fudging modules and each agent take two steps from the location to find new vulnerabilities. First, each agent identifies the current state of the controller and then randomizes the flow sequences or input values of the control messages. So let's take a look at how Delta randomizes each type of control flows. So one example SDN operation that involved the symmetric control flow would be a handshake process between a controller and a switch. According to the OpenFlow specification, this operation should experience total 7 state transitions from state R to state S7. But what if we could manipulate the order of events? So in this case, we intentionally send a get config response message instead of feature response message in response to feature request to see if anything goes wrong. So, and ultimately, we should try other combinations of events to cover all possibility as well. So to automatically carry out such tasks, the channel agent in Delta randomized these symmetric control flow sequences. Next, to first test the asymmetric flow sequences, we can randomize the order of unidirectional messages delivered to the SDN application. For instance, when a controller captures a packet message, which is one of the unidirectional messages from a switch, the controller propagates the message to all the SDN application that are interested in such type of control message in a specific order. In this case, the order of reception is from application A to application D. But we can manipulate the order inversely, so application D can firstly receive the packet message. In Delta, the application agent take part of randomizing such an asymmetric flow sequences. Randomizing the input values of each control message is pretty simple. First, the fudging model in channel agent can manipulate the content of the control messages between a controller and a switch on the fly. For instance, the channel agent can modify the command field of the flow mode message to the undefined value when the controller sends a flow mode message to the switch. And also, the application agents can manipulate the content of the control messages passing within the multiple number of SDN applications. And implementation. Delta now supports 3 open source controllers and 1 commercial controller. And also Delta support 2 prevalent OpenFlow versions in 1.0 and 1.3. For the evaluation of our work, I would like to show the effectiveness of first testing by introducing one of the unknown attack cases that Delta discovered, and then talk about the test coverage and flexibility of Delta. To find unknown attack cases, Delta should be able to determine if each first cycle has triggered any event that matches one of the 7 test criteria that we have defined. As shown in this slide, the test criteria includes controller crash and application crash and so on. With the test criteria, we found 7 unknown attack cases that affect 3 different SDN controllers, as you can see the table in the bottom. So let's take a look at the first one as an example. So here is, using Delta, we were able to discover this attack called sequence and data forge attack, which is effective against the floodlight controller. Here is how Delta discovered it. So first, we select the asymmetric control flow as our target and then click the start button. Then Delta first test different type of control message, asymmetric control messages. And when it comes to first test packet message, the agent manager instruct the fudging model of the application agent to manipulate the order of packet reception. So the application agent becomes the first one to receive packet message. Next, the agent manager orders the host agent to generate network packets to intentionally cause the switch to send a packet message to the controller. The application agent then receives the packet message, and its fudging module randomizes the content of the control messages. After that, the agent hands it over to the next application, which is a topology application. Finally, when the topology application tries to access the manipulated packet message, it causes the controller to disconnect the switch. So this picture shows the impact of this attack. So before the attack, as you can see, our application agent was the last one on the list to receive packet messages. But after the attack, the application agent became the first one. And finally, the topology application caused the switch disconnection. Since such a switch disconnection event matched one of our test criteria, the agent manager was able to detect a new attack discovery. To show the test coverage of Delta, we use Delta to test all the known attack cases against 3 different SDN controllers. And this table summarizes the result. Besides the control flow related ones, there are some attack cases regarding non-flow operations, because most SDN controllers are currently implemented as general application running on legacy operating systems such as Windows or Linux. To confirm the flexibility of our framework, we further tested if Delta works with not only open source controllers, but also the commercial one. So it was able to tell the controller was vulnerable to this application eviction attack or not. This is one of the intra-controller flow attacks that allows an attacker to arbitrarily stop or uninstall the SDN application running in the controller. So as you can see in part A, the flow manager application, which handles the flow rule operations, was originally in an active state, but after the attack, the state of the flow manager became inactive. So finally, since the controller no longer handled the flow rule operations, the entire network became unavailable. In conclusion, in this work, we categorized the known vulnerabilities in SDN that into 3 control flow types and non-flow operations, and we propose an automated security assessment framework for SDN that can replay the vulnerability. And also, we found 7 unknown attack cases by using the black box fuzzing technique in our framework, and we show the flexibility of our system design by evaluating it against the commercial controller as well as open source controllers. So, and Delta is now available as an official ONF sponsored open source project, so please follow this link if you are interested. Okay, thank you for listening. Any questions?